All right, so today we'll look at rotational motion. Okay. Now, before we get started on this, let me go over a couple of things that'll make easy for you to understand this chapter. Okay. So, in rotational motion, what we'll specialize in is what we'll mostly talk about is be related to this. Okay. We'll talk about an object going in a circle at constant speed. So you could be driving in a circular road at constant speed. Okay. Now, velocity is a vector. Okay. A vector has magnitude and direction. Okay. And so I'm just setting you up for this chapter. And when velocity changes, then you are accelerating. Okay, so velocity is a quantity that has magnitude and direction. When velocity changes, you're accelerating. And if you're accelerating, there must be a force acting. Forces make you accelerate. Forces make you accelerate. That's Newton's second law. Okay? So we'll see where the forces come from. So in all the applications. Okay, so here's you're driving on a circular road. When you're here, there's your velocity. Okay. Now let's say a little while later you're there and there's your velocity. Magnitude is the length of this vector. That tells you the speed. The magnitude is the same. The length is not changing. Is anything changing about the velocity? The speed is the same.
No.
Direction is changing. Okay? You see, you were driving east here. Now you're driving almost south. So the direction is changing. You are accelerating. Okay? So whenever you're going around in a circle, even if you're going at a constant speed, you're accelerating because your direction is changing. And it turns out that the acceleration is towards the center of the circle. And it's called centripetal acceleration. And how big is the centripetal acceleration? It's your speed square divided by the radius of the circle. R is the radius of the circle. Okay, I'll draw that. Okay. All right, so if you want to go around in a circle at constant speed, this is the acceleration, so there must be a force that's acting in that direction to make you go in a circle. And that is called a centripetal force. Okay? So to make you go around in a circle at constant speed, you need a force that's acting towards the center constantly. Okay, so when you're here, the force is acting this way. When you're here, the force is acting this way. So let's look at a couple of examples. Okay. Here's the sun. Here's the earth. The earth, by the way, is going at constant speed. It's going in a circular orbit. And the radius of the earth is about 92 million miles. The speed of the earth is 30 kilometers per second. Okay, so the earth is going around at 30 kilometers per second, which is roughly 20 miles a second. The earth goes from here to, let's say, Palm Coast in 1 second. That's how fast the earth is going. The speed of the earth is not changing, but is it accelerating? Yes, it's accelerating because the direction of the velocity vector is changing. So the earth has a centripetal acceleration, which needs a centripetal force. So where is that force coming from?
Gravity.
Yep. sun's gravitational force is what's providing the centripetal force. Okay? So that's what makes the Earth go around the sun. Okay. Here's another example. Exactly the same example. So here's the Earth. We got a bunch of satellites going around the Earth. So we'll talk about the International Space Station. The International Space Station is going around at 8 kilometers per second. That's 5 miles a second. The International Space Station goes around the Earth from here to Ormond Beach in 1 second. Okay. Is the International Space Station accelerating? It is accelerating. Why is it accelerating? Because the direction of the velocity vector is changing. Okay, even though its speed is not changing. And what is the direction of the acceleration? It's the centripetal acceleration. So there's a centripetal force acting on it. And what gives it the centripetal force? Gravity, the Earth's gravity on it. All right. All right, so if you understood that, then we'll apply these concepts to biological systems. Okay. So this thing is called uniform circular motion. It's called uniform circular motion because your speed is not changing, but the direction of the velocity vector is changing. Okay. Now let's talk about, so let's say you're going on a circular road, you're driving on a circular road at constant speed. Again, you're accelerating, your centripetal acceleration, so there must be a centripetal force. Okay. What is providing the force this time? You're driving on a flat road. What? I'm sorry? Friction. It's okay. So your car is moving in this direction. Your car is not moving in this direction. So it turns out it's the static friction force that is providing the centripetal force. Okay. Your tires have to be sticky to make a turn. If your tires are frictionless, you couldn't make a turn. You can turn your steering wheel all you want. If your tires weren't sticky, you would go straight. Okay. Here's another example. Okay, so again, we're talking about uniform circular motion, objects going in a circle at constant speed. Okay. Let's tie a ball to a string. You can whirl the string around, and the ball will go in a circle. Okay. So let's make it go around in a circle. What is providing the centripetal force? The tension in the string is providing the centripetal force. Okay. So let's do the following. Let's make the string snap. What will happen?
That ball will start flying.
Yeah. So the instant you snap the string, there's no tension, there's no centripetal force. The ball won't go in a circle anymore. It'll just fly straight.
So it would travel perpendicular to the last centripetal force applied?
That's right. So the instant the string snaps, it'll go straight, perpendicular to the radius, yep. Or tangent to the circle. So here's a thought experiment for you guys. Now there's a little crank to that. So here's the sun, here's the earth. Go home and flip a switch and make the sun vanish. What will happen?
The earth will start flying.
It'll go straight. Okay? So as soon as you remove the source of the centripetal force, the object will go in a straight line. All right? All right, so those are the concepts we're going to apply to biological systems. Okay? So we'll talk about rotational motion. By the way, I was changing the slide just a minute ago and it didn't synchronize properly, so let me make sure I have all the slides. All right, looks like I do have all the slides. Okay, good. All right, so we'll talk about rotational motion. Okay, so here's a ride where these guys are going in a circle and they're going at constant speed. Okay. And that is called uniform circular motion. So uniform refers to the fact that your speed is constant, and circular motion, of course, telling you that you're going in a circle. Okay. So even though an object is in a uniform circular motion and is moving at constant speed, the direction of the velocity vector is changing, and so the object is accelerating. Okay. And that acceleration is called a centripetal acceleration. Why is it called a centripetal acceleration? Because the acceleration is pointing towards the center of the circle. And the magnitude of the acceleration is v squared by r. So smaller the circle you're going in, greater your acceleration. Harder it is to go around in a small circle. Faster you're going, greater your acceleration. It's hard to make a turn fast. Okay, you guys know all of that. Yeah. So, and to make anything accelerate, you need an force. Okay, and in this case, since the force has to be directed the same direction, it's called centripetal force. Okay, so in uniform circular motion, the acceleration is directed towards the center of the circle. We call it centripetal acceleration. So to make these guys go in a circle, there's tension in the string. That cable had better be strong. Okay? It needs to be strong enough to, support your weight and all that. All right, so let's we'll apply this to you walking. Okay, when you walk, here's what happens. Okay, so here's your foot, and your center of mass is there, and your center of mass pivots over this foot. And look at that. Your center of mass is going in a circle. Okay. And so essentially goes at a constant speed. So this is part of a uniform circle. Okay. Well, okay, if v is the speed, to make you go like that, so you can walk like this, you need a centripetal force. Well, where is the centripetal force going to come from? Here is the centripetal force. Here's your weight acting down. So if we're drawing this diagram at this point, your weight is acting down. And then the ground is pushing you up, so there is the normal force. Okay, so the centripetal force is the sum of these two. We'll take this as the positive direction, so it's this minus that. So let's make sure that we understand this. So the centripetal force is your weight minus the normal force. And that should equal your mass times the centripetal acceleration. All right. Remember, the centripetal force is a force acting towards the center of the circle. And that is coming from these two forces. This guy is acting, your weight is acting down, and your normal force is acting up. Yeah. All right, your weight, let me write this down. What's your weight? Your weight is your mass times gravity. That doesn't change. There is the normal force. That's equal to your mass times your normal. All right, so let's look at what's happening. R is the length of your leg. Okay. Let's say, can you walk faster? Can you walk at different speeds? So if you walk faster, what happens? Well, gravity doesn't change, your mass doesn't change, the length of your leg doesn't change, this doesn't change. So if this is to become bigger and this doesn't change, how can this become bigger? Meaning you walk faster. This has to become smaller. So your steps become lighter. You're not pressing against the ground as hard. This becomes small. What is the smallest it can become? What is the smallest it can become? 0. The smallest it can get is 0. That'll tell you fastest walking speed. And your fastest walking speed is about 4 miles an hour. All right? All right, so is it 4 miles an hour? So let's see. Okay, it's 6 miles an hour is your walking speed, except that at 4 miles an hour, running becomes more efficient. So you switch from walking to running. Okay, and we'll talk about that. So your fastest walking speed is roughly about 6 miles per hour. All right, I hope you guys understood all of that because that's what the chapter is about. Okay, so the maximum walking speed which you can the maximum speed with which you can pivot on or turn a corner is determined by the force of static friction. So this is for turning. Your maximum throwing speed is determined by the torques on your shoulders as it rotates. So we'll talk about those various things. Okay. So for instance, here's the picture of your arm. So let's say when you're playing tennis, here's what happens. Your arm rotates about your elbow. Okay. To make your arm rotate, you have to apply a torque. Okay. This muscle is contracting and you get tennis elbows from straining that tendon. Okay. So in many sports, your muscle needs to exert large torques to hit an object. Okay. So when you're playing tennis, to hit, and here's another problem, the longer the racket you use, the greater the torque you have to apply to that when you hit the ball. When you hit the ball harder, you have to apply a greater torque. The stress of exertion can lead to injury such as tennis elbows. You're hurting that tendon. Yeah. So now we'll mention centripetal acceleration. So here an object is going in a circle. It's going at uniform speed. So its speed is not changing, but you can see that the direction of the velocity vector is changing. So hence it has an acceleration towards the center of the circle. Okay. And this acceleration is called centripetal acceleration. Okay. So an object in uniform circular motion is accelerating, yeah, because the velocity vector is changing. Okay. Here's the magnitude of the acceleration. The acceleration is the speed square divided by the radius of the circle. Again, like I said, smaller the radius of the circle, greater your acceleration, greater the force you have to apply. So at the same speed, if you're going in a smaller circle, that's harder to do. For a given circle, the faster you're going, that's harder to do. Okay? So this is the magnitude of the centripetal acceleration. So here's a quasar carnival ride. Okay. So when the ride first starts, this pod is horizontal and pointing down. You get in, and then as it gets faster and faster, see the pod gets vertical. Okay. And so in these rides, you can experience centripetal acceleration as great as 20 meters per second squared. So the acceleration towards the center, A, can be 20 meters per second squared, which is 2 times G. G is 9.810 meters per second squared. So what that means is the force on you is twice your body weight in that direction. Okay. And so that's what's the exciting part of the ride. You're feeling a force that's twice your body weight, and there's gravity. So the total force on you is in that direction. Okay? All right, so this gives you this. So the centripetal acceleration. The centripetal acceleration is v squared by r, and v, the speed is r times, and centripetal acceleration v squared is that, and v is square root of r times centripetal acceleration. Okay. Again, you don't have to be able to calculate all of this. So v, the speed at which you're going is square root of the centripetal acceleration times r, there times that, and the radius is 5 meters. 5 meters is, so these rides are from here to the wall. That's how big those rides are. Okay? You're going at 10 meters per second. You're going at 10 meters per second. 10 meters per second is how fast Usain Bolt runs. Okay, so you go in those rides and you can feel, you can experience how fast Usain Bolt runs. Okay. This is the period, how long it takes for you to go around the circle once. Okay. That is 2 pi r is the circumference of the circle, and that's your speed. So it takes you about 3 seconds to go around that circle. Okay. That's what that is saying. All right, so we'll do a couple of things with these diagrams. So the period is 2 pi r by v. Period is 2 pi r by v, and the centripetal acceleration is v squared by r. Okay, so what we want to do is rank in the order of the smallest to, from the largest to smallest period of the motion. So which takes the longest of these guys? You're going in a circle, and we'll also find the greatest centripetal acceleration. Okay. So let's find the centripetal acceleration for this guy. Centripetal acceleration for this guy is v squared by r. For this guy, so let me, centripetal acceleration, v squared by r. For this guy, it's 2v squared by r, which is equal to 4v squared by r. So the centripetal acceleration for this motion is 4 times the centripetal acceleration for this motion. You guys understanding this? Okay. For this guy, it's v squared v squared by 2r. So the centripetal acceleration is half of this guy. For this guy, it's 2v squared divided by 2r. So 4v squared, that's 4 divided by 2. So it's 2v squared by r. So you see the centripetal acceleration for this motion is the greatest. Okay. For this guy, the centripetal acceleration is this, twice this. Okay. So the centripetal acceleration for this guy is the greatest. Now let's do the period. So the period for this guy is 2 pi r divided by v. For this guy, it's 2 pi r divided by 2v. So the period for this guy, 2 pi, is half the period for this guy. So if this guy takes 4 seconds, this motion only takes 2 seconds because he's going twice as fast. The same radius. Okay. For this guy, it's 2 pi times 2r divided by v. Okay, so this is 4 pi r divided by v. So this guy this guy is taking twice as long as this guy. Okay, so, and that makes sense. The circle is bigger and you're going at the same speed. You're traveling twice the distance, so you're taking twice as long. How about this guy? The period is 2 pi times 2r divided by 2v, which is equal to 2 pi r divided by v. Well, the circle has become twice as big, but you're going twice as fast, so you're going at this, it takes you the same amount of time as this guy. Okay, so these two times are the same. Okay. And so this shows you the centripetal acceleration and the period for those various orbits. Okay. So there's test questions on that. Okay. All right, so we saw that to make you go in a circle, you need a force acting towards the center, and that's called the centripetal force. F for force, the subscript C telling you it's a centripetal force, and the magnitude of the centripetal force is your mass times your centripetal acceleration. Okay. So even though you're going at constant speed around a circle, you need a force towards the center. Okay, so here's Tarzan swinging on a vine, and you see his center of mass is going in a circular orbit. Okay. Now, in this problem, his speed is increasing as he's falling down, but we'll apply this just right here near the bottom. His speed is constant. Okay, so we'll apply these principles there. So at the bottom, so here's the speed. You need a centripetal force in that direction. Okay. And where's that force coming from? Well, here's Tarzan's weight, and here's the tension on the vine. Okay, so the tension minus the weight is equal to the centripetal force. Okay. And in fact, it turns out the tension here is the greatest. So if you're swinging on a vine, and if the vine were to break, that's when it would break, when you're at the bottom of the swing. Okay. So here's a competition that you've seen, a hammer throw. Okay. Let me remind you of our previous example here. So let's say you attach a ball to a string and you're whirling this ball around. What happens when the string cuts at this point? What will happen? If the string were to snap at this point, what would happen? It would fly straight. So in a hammer throw, what you're doing is you're accelerating this, you're swinging it as fast as possible. And if you want to throw the ball in this direction, when the ball is here, that's when you let go of the hammer. And then it flies. The greater the speed it's flying at, the further it'll fall. Okay? And that's the idea of the competition. Okay, so so to make it go in a circle, you have to apply a centripetal force. Okay, and greater the speed it's going at, greater the speed it's going at, the radius is fixed. Okay, so to make a larger radius, so you have to apply a smaller force. You have to be a bigger guy. A bigger guy, a taller guy is more likely to win this thing. Okay? All right, so you're swinging it in a circle. You have to apply a centripetal force. You got to be strong. The stronger you are, the greater the velocity you can launch it with. And then if you want to throw it in this direction, when it's like that, that's when you let go and it'll fly over and go as far as possible. Okay. So that's the competition. So when the hammer is heading in the right direction with enough speed, the man lets go. And with no force acted towards the center, the hammer will stop going in a circle and fly along that tangent. Yeah. Okay, so here's something that you do every day. Okay, so let's say here's a four-way intersection. Yeah. So here's a four-way intersection, and you turn to go to that road. Okay, so here's, you're going on a circular road in a circular arc, and to make you go in a circle, you need a centripetal force in that direction. Okay. And see, your car is not moving in this direction, so it's a static friction force. Okay. That's because your tires are sticky and providing the static friction force. Now this force, static friction force, has a maximum value because it's providing the centripetal force mv squared by r. R is the radius of the circle and v is the speed at which you're going. So since this has a maximum value, there's a maximum speed at which you can make a turn. Okay. So here's a top view, here's a top view, here's a side view. It's the static friction force that's providing you the centripetal force. Okay. So the car doesn't complete a full circle, but it's in uniform circular motion for a quarter of a circle. Okay. So we'll talk about this. If the road were frictionless, if your tires weren't sticky, if the road were frictionless, like on a very icy road, turning the steering wheel would have no effect. The car would just go straight. So if it was frictionless and you're trying to turn, you can turn all your steering wheel all you want. All you'll do is end up going straight. Has anybody here experienced that? Have you lived up north? All right, so you need a friction force to make a turn. Okay. Now, when you have the static friction force, like I said, this force is being provided because of the stickiness of the tire and to the road. And when you make a turn, every time you make a turn, you're leaving a little rubber on the road. Okay. So we'll see in a second. So how do you and your tire wears down. It treads wears. So over time, you lose much rubber. Okay, so what do we do? And this cost the country billions of dollars a year. So how can you prevent that? Okay, for these intersections, there's nothing you can do. But on exits on the highway, what do? They make the bank the road. So we'll see in a second, if you go on a banked road, and if you go at the speed that is marked on the exit, you don't need any friction. You don't leave any rubber. Okay? And if you don't need any friction, what does that mean? You can exit that exit even in very icy conditions. Okay? So we'll see that. Okay, that's why the roads are banked. So it saves the country billions of dollars, so you don't need this friction force. Okay. All right, so you're turning corners. Now we're doing it at an intersection, and you're using friction force, static friction force. Okay, so there is the static friction force. So this is the maximum static friction force, and we'll calculate that. So the maximum static friction force will give you the maximum speed at which you can turn. Okay, so the maximum static friction force. And by the way, the maximum static friction force, is equal to mu s, the stickiness of the tires, coefficient of times the normal force, and the normal force is equal to your weight. Okay, mu s times mg. Okay, so the maximum static friction force is providing that. Your maximum static friction is mu s times mg. So if you solve this, the maximum speed at which you can make a turn is how sticky your tires are times g times the radius of the circle. So the bigger the circle you're going at, the faster you can go with the same tires. Okay? The smaller the circle you're going at, the smaller your maximum speed. If you go faster than that, what will happen? What will happen? What? No, you skid. You don't go in a circle. You're, what's that? Yeah. Yep, skid into a tree or skid off the road. Okay. Your your car will go in the bigger circle on its own, whether you want it or not. Okay, so this tells you the maximum speed you can go at. And you see, I mean, you might have not known these equations, but you intuitively know this. You know, you slow down intuitively when you come to a curve and so on. And you intuitively know the maximum speed you can go at. Yeah, so your intuition is quite good. I'll show you another pretty amazing fact. Okay. So, well, I'll tell you now. Okay, so if you do the following experiment, let's say you're on a treadmill. Okay, you start walking on the treadmill, and we'll increase the speed of the treadmill. Okay. So you make the treadmill go faster and faster. So you're walking faster and faster. And then it'll come to a point, you'll come to a speed where you'll automatically switch to running without you consciously doing it. Do you know when you automatically switch to running? When it becomes more efficient to run. Your body knows, and it automatically switches to running. Okay. All right, so there is the maximum speed to making corners. Okay, so if you want to, so this is the maximum speed you can go at. That's determined by the stickiness of the tires. What if you want to make a turn faster? Of course, you want to do that in races. You want to make it turn faster. So what you have to do is you bank the road. Okay? And this will allow you to make the turn faster for the same radius. Okay? All right, let's see how that happens. Okay. So, by the way, those exits on the highway, this is so here's what that angle is. So here's a banked road. This angle is theta. Okay. And so if this is your car, now I'm drawing a side view. You're coming out, and that's the speed at which you're coming. Okay, so in the road, and the exit road is banked at that angle. If you go at this speed, and that's the radius of curvature of the road, so this road is part of a circle, and there's the center of the circle, and R is this radius. Okay. If you go at the speed marked on the exit, you won't need any friction. So if you're up north in icy conditions and you want to come out of an exit, you go at that speed, you won't slide off the exit.
You're talking the yellow signs
Huh?
on exit, the yellow speed limit signs, the recommended speed.
The recommended speed, yep.
So that's the speed at which any lateral force is minimized.
It's zero. Any friction force is zero. All right. So if you can tell me something nice about this equation, something amazing about this equation, I'll buy you a soda. Do you notice anything very interesting about that equation? What are you driving?
A car.
Well, is there any information about that in the equation? That equation is the same for a car, a semi, or an SUV. It doesn't matter what you're driving. It's independent of the mass. That sign is not, you don't have a different sign for a semi or anything. Amazing, all right? So this is independent of the mass. All right, so let's see how that thing works. Okay. All right, so here's the banked road. Okay, here's a top view. Here's the exit. You're going in a circle. Okay, to go in a circle, what is it that you need? You need a centripetal force in this direction. Okay, and let's see where is the centripetal force coming from. What we want to do is we don't want to use any friction. Okay, because we want to be able to come out of the exit even in the most icy conditions. Okay, so so the road exerts a normal force on the car. The normal force is perpendicular to the road, okay? And here's the weight of the car, okay? So remember, you need a centripetal force in this direction, and this component of the normal force is providing the centripetal force. So this component is providing the centripetal force, and this component of the normal force is balancing the weight. So what is happening is, when you're driving on a flat road, the normal force is equal to your weight. Normal force is equal to your weight. When you drive on a curved road, the normal force becomes greater than your weight. And part of the normal force, this component is balancing your weight, and this component of the normal force is what's providing the centripetal force. Yeah. And of course, if you go faster than that, then you'll need friction force. So, I mean, if an exit is marked at 35 miles an hour and you go 50 miles an hour, then you have to use friction force. You have to leave rubber on the, okay? What happens if you go slower? Then too, you have to use friction forces, except that the friction force is in the opposite direction. Okay. We have a fantastic road here. Have you guys ever been inside the speedway? Yeah. This bank angle is 30 degrees. It's absolutely amazing. Okay, you have to go at 90 miles an hour if you don't want to slip down here on icy conditions. Okay. You go less than 90 miles an hour, you need friction in that direction, and you go more than 90 miles an hour, you need friction in this direction. Yeah. All right, so if you don't want to use any friction on a road like this, this is the angle, okay? This is the speed at which you need to go. So that's what it's given here. Tan theta is V square by GR. R is the radius of the circle, G is the acceleration due to gravity. So if the road is banked at that angle, that is the speed at which you need to go, so you don't use any friction. Okay? And so all those exits are banked at that angle, and if you go at the marked speed, you leave no rubber on the tire. I mean, no rubber on the road. And that saves the country billions of dollars. Yep.
So, I'm gonna try this today.
Mm-hmm.
If I'm driving down the road on a motorcycle,
Mm-hmm.
at a constant rate,
Mhm.
motorcycle's dead upright.
Mm-hmm.
If I do that speed around that bank corner of the motorcycle in relation to the surface of the road,
Mm-hmm.
will be perfectly perpendicular.
And that's right. Mm-hmm. You won't have to lean into it, my friend. Yeah. All right, so if you want to use a friction force, so when you make a turn on a flat road, you have to lean in. Okay, so you have to lean in such that I have to answer this, but all right. So we'll figure out the angle at which you have to lean in. Okay, here's the normal force that's balancing your weight. And here's the friction force that's providing you the centripetal force so you can go in a circle. Okay, you have to lean in such that this friction force, okay, this angle, this friction force is equal to that side. There's the normal force. Okay, that's the angle of your lean. Okay, so we'll give you the precise angle in a second. Okay, so here's the guy making a circle. Here's the center of the circle. There's the friction force that's providing you the centripetal force. Here's the normal force that's balancing your weight. Okay. The faster a cyclist goes around the turn, the more he has to lean. The faster you go around a circle, the greater the friction force. So the greater the friction force, more the lean angle. Okay. The stickier the tires, the faster the cyclist can make a turn. Yeah. So the stickier the tire, a less sticky tire around the same turn, the maximum speed is smaller. The stickier your tire, greater your maximum speed. That's what we're saying. Okay, so let's, now I'll give you an expression, and that'll show you this. Okay, so here's a cyclist going around the circle. There's the lean angle, theta. Okay? And this formula, in a second, you'll see that it's identical to this formula. And here, angle is theta. Okay, so you'll get the same relationship. Tan theta is v squared by gr, except that here theta is this angle. Okay, so the friction force is providing the centripetal force, and the normal force is balancing your weight. Okay, and so if you so the friction force is equal to that, and tan theta is the friction force divided by that. So tan theta is the friction force divided by the normal force, which is equal to that. So tan theta is v squared by gr. Exactly the same relationship as the one before. The greater the speed you're going at, tan theta has to be greater. So you have to lean further so that this number is bigger. Smaller the circle you're going in, greater your lean angle. Okay? So that's what that equation tells you. The maximum value of the friction force, the maximum value this can have, is dependent on the stickiness of your tire times the weight. Okay. So the maximum lean angle is given by the stickiness of your tire, and the maximum lean angle tells you for a given speed, there's the minimum circle that you can go on. That's the smallest circle you can make a turn at. If you make a turn smaller than that, you'll slip and fall. Okay? And for a given turn, you can calculate the maximum speed once you have the maximum lean angle. Okay? So you want to be able to lean more than you want stickier tires. Okay? So that's what racing tires are. They cost you more and they wear faster. But they allow you to make turns faster. Okay? All right, I gotta speed up a little. Okay, now we'll calculate the fastest walking speed. Okay. So again, like I said, your center of mass is going in a circle, and at the top, here are the forces acting on you. Here's your weight, and here's the normal force. Here's your weight, and here's the normal force. The net force is in this direction, and the net force, mg, your weight, minus the normal force is mv squared by r. Okay, and so the faster you're walking, everything else is constant. The normal force is becoming smaller. Okay, that's how you walk faster. Okay, and the smallest this can be is 0. So the fastest walking speed is when this is 0. Okay. So in walking gait, your body is in a circular motion as you pivot on your front foot. As you pivot over your front foot, your body is in a circular motion. Yeah. And there is the force, the weight minus the normal force. Weight minus the normal force is providing the centripetal force. Okay. And the fastest you can walk corresponds to the normal force being 0. Okay. And of course, normal force cannot be 0, so that, that just gives you an upper limit. Okay. Yes.
I was trying to figure out how is normal force.
Yeah. Then if normal force could be 0, then you could walk on water. Okay. So since you can't walk on water, your normal force will never go to 0. All right. So the normal force becomes smaller as you walk faster. But n cannot be less than 0, or it can't even be 0. But so the maximum walking speed occurs in the limit of n going to 0. So that tells you what is the fastest you could walk. Okay. You could possibly walk. So if this goes to 0, this is 0. W equal to that. W equal to mg equal to that. And so your maximum walking speed is square root of g times r. G is the acceleration due to gravity. Okay. So that is smaller on the moon. You could walk faster on the moon. R is the length of your leg. The taller you are, the faster you can walk, the faster your maximum speed. Okay? So the maximum walking speed is set by R, the length of your legs, and G. Yeah. Giraffes, which have long legs, can walk at high speeds. Yeah. Animals such as mice with very short legs have such low maximum walking speed that they rarely walk. So if they're moving, they're running. Yeah. All right. For humans, the length of the leg is approximately 0.7 meters, giving the maximum speed of about 6 miles per hour. Yeah. Most people make a transition to running gait at about 4 miles per hour because running becomes more efficient then. Okay, so let me show you a graph right now. So this graph shows you C is how much energy you're spending per kilogram per meter. What this is telling you is how much energy you would spend per meter of travel, okay, per distance covered. And this is at various speeds. And you see at this speed, this is in kilometers per hour, so at about 7.2 kilometers per hour, walking costs you more than running. Running, the energy spent per unit distance is almost constant. Okay? Walking is more efficient at slow speeds. It's more expensive at higher speeds. So this is what happens in a treadmill. If you go on a treadmill and you start increasing the speed of the treadmill, at this speed, your body will automatically switch to running. Okay. Your brain is very smart. Yeah. So if we are on a treadmill whose speed is gradually increased, the point at which we spontaneously switch from walking to running coincides with the moment when it becomes more energy efficient. Okay. All right, so when you walk, so we got the maximum walking speed. Okay. So there's the maximum walking speed. Yeah. All right, so walking versus running. When you run, okay, running is more efficient at higher speeds because when you run, you're loading your springs. What are your springs in your body? I'm sorry? Tendons, okay, your Achilles tendons and other tendons, they compress and they store energy, and then they'll give back that energy to propel you forward. How much energy do the tendons give back? 90%. Okay, that's why, and kangaroos have huge tendons and they can run long distance, they can go efficiently a long distance. All right, running can be modeled as a spring mass system. So this is your body center mass and there's the spring. Okay. At slow speeds, the pendulum-like mechanics of walking are efficient. As speed increases, the up and down motion of your central mass becomes too costly, energetically costly, and mechanically unstable. So you switch to running. Okay. So here's what's happening during running. Here's a model. Okay, so here's your body center of mass. As you lay down the foot, as your heel goes down, it's stretching the tendon, and then this can propel you back up. Okay. So you see here, your muscle is not doing any contraction, and the energy stored in the tendons is being propelled back. So this is you're not using any energy. This is hardly using any energy, and this is very efficient. So energy flow is your gravitational potential energy got converted to spring potential energy, then back to gravitational potential energy. That's what the energy flow is. Okay. Here, when you're climbing stairs, for instance, okay, so here's you're getting ready to climb stairs. The muscle had to contract and had to do work. Okay. And the tendons stretched, and when you lifted your heel up, you propelled yourself forward. Okay, so this energy got converted to gravitational potential energy. Okay, so you have to do work to climb stairs, and when you're on level motion, okay, it's efficient to use the energy stored in the tendons. Okay, and this is when you're climbing down, you're walking downhill, or you're walking down steps. Okay, so here's gravitational potential energy, and when you step down, you stretch the tendon, but you're going down, and the muscle contracted and had to dissipate energy to get your tendon back to its original shape. Yeah. So you're losing energy in heat. Okay. So to stretch a tendon, the muscle must actively contract and generate force. So when the muscle contracts, it stretches a tendon. Okay. So the work done by the muscle is used to strain the tendon and store energy in the tendon. Okay. During running, tendons act like springs, storing energy when stretched and releasing it during recoil. Okay, so tendons store energy when they're stretched, and when they recoil, they'll give that energy up. Okay. To help body, this process helps make running more efficient by reducing the amount of work the muscles do. So when you're running, when you land and your ankle hits the ground, this tendon is stretched, and then this will give you the energy back to propel you forward. So, yeah. So using your tendons when you're running makes it an efficient process. Okay. We have a very precise, intuitive perception of energy efficiency of a particular style of movement. Okay, so we know exactly, depending on our speed, what is more efficient. Okay. So about 2 meters per second, for most of us, running is more efficient. Okay. So if you try walking faster than 2 meters per second, your body will automatically switch to running. Okay. For most people, the transition from walking to running happens around 2 meters per second. That is 7 kilometers an hour, or 4.5 miles per hour. Studies show that energy cost per distance, so that's how you calculate it, how much energy you're spending to go a mile. Okay, energy cost per distance. Oxygen consumption per meter, that's how they measure it. Okay, of walking rises steeply about 2 meters per second. So walking, you're spending much more energy, about 2 meters per second. Okay, has anybody here used a centrifuge? You use it for your work? Yeah. Okay. All right, so let's do the following. Let's take a glass of water, and we'll throw in some sand. And stir it up real good, and then let it sit. Okay. All these particles will eventually settle down. Okay. So I'm just using sand particles here. What you really want is, let's say, if this is blood, and there's your blood cells and all that. So if you take a cup of blood and let it sit, all these particles would settle. But these particles would take days to settle down. Okay. If you take sand, of course, the bigger particles would settle down first, and then these particles would settle. And even sand, you can take a dirty cup of water, it takes a while for the water to clear. Okay. What a centrifuge does is, it makes the settling process happen much, much faster. You've used a centrifuge? Yeah. How does it do that? What would make the settling process happen faster?
It rotates the bottom.
Okay, so the settling process would happen faster. What makes it settle in the first place?
It's greater mass than the surrounding substance.
Gravity, the force of gravity. Okay.
Wouldn't that be centrifugal force?
Yeah, so gravity makes it settle faster. So if you could make gravity stronger, it would settle faster. And that's what this does. it effectively increases gravity by a huge amount. So in blood, if things would settle in days and weeks, it'll make it settle in minutes. Okay, yep.
I believe we're missing that last line.
Which one? This,
Before that. It was another
This one.
That one.
yeah, I added that 2 minutes before I came.
Okay.
10 minutes after the class is done, I'll put it on. All right. I'm changing stuff all the time, so. Okay, so a centrifuge will make things settle faster. Okay? So, in principle, mixture of oil and water spontaneously separate, as do cream and milk, with the less dense liquid floating on the denser liquid. However, separation is slow if liquids have been thoroughly mixed. Okay. Small particles suspended in liquid in a test tube also separate by density. So the densest stuff will be at the bottom, and the next dense stuff, and so on. Okay. More dense particles sink through the liquid faster than the less dense particles of similar size. Okay. Yeah. So for microscopic particles such as cell components, the settling time, even under ideal conditions, may be days or weeks. So if you take blood, it'll take days or weeks for the particles to settle down. Okay. Under real world condition in which diffusion and temperature variation cause some mixing, so temperature will cause some mixing, and you may never have settling. Okay. So microscopic particles may never settle. But you have to separate those components in bloods to do whatever testing you're doing. A centrifuge drastically speeds up the separation process by creating an extremely strong artificial gravity. Okay. So, yeah. So when the particle is, here are the forces on a particle, here is the force of gravity, and there's the drag force, okay, when you're in a liquid. So the terminal velocity, okay, the same terminal velocity, when you jump off a plane, you have terminal velocity. When you reach terminal velocity, the drag force is balancing your weight. Okay, so if you jump off a plane like this, your terminal velocity is 180 miles an hour. When you jump off a plane like this, your terminal velocity is about 120 miles an hour. Okay. So the terminal velocity for those particles, the terminal velocity is the particle density minus the liquid density. Okay, so if your particle density is the same as the liquid density, you couldn't separate the particles. Okay, you can only separate different density particles. So times the acceleration due to gravity. So if you want this terminal velocity to be greater, this is something you can't change. That's a property of the material. All you can do is change this, make the gravity artificially stronger. And all you do is spin this thing like crazy, and effectively you're changing the acceleration due to gravity. So in a centrifuge, the effective gravity is the speed at which you're going around divided by the radius. So you can make it go very fast, okay, and increase the effective gravity tremendously. Okay. You can increase the effective gravity by almost 1,000,000. Okay. Now, if you're spinning it very fast, you got to make sure that it is balanced. This can't be heavier than this. You can't have one tube filled and the opposite tube empty. That would become unstable. Okay. So you have to centrifuge an even number of tubes. Okay. And they got to be at the opposite ends. In an ultra centrifuge, spinning at 75,000 RPMs is no big deal. And you can separate stuff quite fast. Okay. You can test this out. You can make your own centrifuge. do a vertical spin like that, and your hands will get thicker because your blood is collected in your hands. Okay, and you can actually see it. So go test it up. Make your hands bigger. Make your hands swell up. All right. All right, guys. So that's it for